Well, we're going to finish up this module with a short discussion of pendulums. We're not going to go into nearly as much detail about pendulums as we could, but when you think of a pendulum, something that hangs from a string and swings back and forth, the concepts are going to be the same as a lot of the same type of concepts that we've already discussed with the mass spring system. At the bottom of the swing, it doesn't have any height associated with it. It's at the lowest possible point. So here, at this point of the swing, your potential energy is going to be equal to 0, and your kinetic energy is going to be at its maximum. Okay? Then when the pendulum gets up here to its highest point, which again is going to be called the amplitude, up here your potential energy is going to be at its maximum and your kinetic energy is going to be equal to 0. Now, we could do all sorts of calculations with potential energy and kinetic energy with pendulums, just like we did with springs, but we're not going to. Would be the same type of ideas. In fact, in my physical science class, and maybe you've done some experiments like this in your younger years, I actually have my physical science students do an experiment where they're trying to figure out what it actually is that affects the period of a pendulum's swing. And so I have them do 3 different things. I have them change the mass, I have them change the displacement, meaning how far away are they pulling it from the straight down vertical position, and I have them change the length of the pendulum. So once they do that, what they end up discovering is that it doesn't matter how much mass they have hanging on the end, and it doesn't matter how far up they pull it within a reasonable amount. The only thing that matters is how long the string is that they have their pendulum made with. Now, I don't go into this with my physical science students because most of them are, they've not had the advanced math that you've had, but your book mentions this, and when I have them do the lab, I have them be careful not to pull their pendulum up too far and let it go because it doesn't work as well that way. The reason for that is because if you get a displacement greater than about 20 degrees from the vertical, it will no longer exhibit simple harmonic motion. So that angle of displacement can't be very large. It has to be 20 degrees or less. So again, the mass of the pendulum bob doesn't matter. How far you displace it doesn't matter. The only thing that matters is how long the pendulum itself is. And the period of a pendulum then is given by the equation 2 times pi times the square root of the length of the pendulum over gravity, acceleration due to gravity. All right, so let's just do a real quick example together. Example 10.5 says, what is the length of a pendulum of a standard grandfather clock? Now, in order to work this problem, you had to read what he'd already told you about grandfather clocks previously. And that's that when it goes tick, that's 1 second, and then it comes back and does tock, that's going to be another second. So the period of that grandfather clock is actually going to be 2 seconds, and we're going to go ahead and give that 3 significant figures. So I have a tick, tock, tick, tock. Okay, that's how a grandfather clock sounds when it goes, and it's going to make a tick on one half and a tock on the other half. So a complete period is when it goes there and when it goes back, and so that's 2 seconds. So then I've got 2 times pi times the square root of the length, which is what I'm trying to find, over gravity, which is 9.8 meters per second squared. Okay, and hopefully you recall how to work this kind of problem. This is an L. I'll make that a cursive L so that it doesn't look like a 1, so we know that that definitely is the variable that we're using there. Hopefully you remember how to work this. You're going to first divide both sides by 2 pi, so I would take 2.00 seconds divided by 2 pi equals the square root of L over 9.8 meters per second squared. You're going to then square both sides, And then once you do that, then you're going to be able to solve the rest of this, okay? So just a reminder of how to do that algebra. When you solve that, you're going to get a length of 0.99 meters, okay? That's going to be the case, obviously, assuming that we're on Earth. If we were on a different planet where the acceleration due to gravity was different, then obviously the grandfather clock would have to have a different length to have that same period. Okay, so we'll finish up this module, and then we'll be ready to move on to something completely different.